Okay, section 11.1 is simplifying radical expressions. So I'm going to start by reviewing some of the basics, which you've seen before. The product property of squares says for any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of the product ab is equal to the product of each square root. So what does all that mean? So if I have a product under a radical, I can simply say, well, if I take the radical of the first number, multiply by the radical of the second number, it's the same as multiplying them first and then taking the square root. In other words, the square root of 9 times 5 is the square root of 9 times the square root of 5. I know the square root of 9 is 3, so I can simplify that using this product property. So let's do a few more examples using the product rule to simplify square roots. If I have the square root of 12, now my key here is to find perfect square factors. So I want factors of 12 that are perfect squares. Perfect squares are numbers like 1, 4, 9, 16. So I'm looking for these kinds of numbers as factors of 12. 6 times 2, neither of those are perfect squares, but 4 times 3, okay? Then I can take and use my product rule and break this into 2 radicals. And I know that the square root of 4 is 2, so 2 root 3 is my simplified square root. Let's try another one. Square root of 90. Again, looking for numbers like this, perfect squares, they keep going. You should know them. Would be the square root of 9 times 10. Again, using the product rule to break this apart, and I can say 3 root 10. So pretty simple. The other thing I can do with the product rule is I can use it to multiply radicals. So if I have the square root of 3 times the square root of 15, my product rule says that I can put those both under the radical together. 3 times 15 is 45. Now, I've got to look at what my result is here and see if there are any perfect square factors. 45 is 9 times 5, so I can simplify this to 3 root 5 as my final answer. So that's pretty much it with multiplication. Now, I'm going to take a minute here to talk about simplifying variables. The square root of x squared. Let's look over here. The square root of 9 is 3 because 9 is 3 squared. So the square root of x squared should be x. However, if x equals -2, let's look and see what would happen. The square root of x, which is -2 squared, should equal -2. But we all know that the square root cannot be negative. That has to be a +2. So since variables, we don't know if they're positive or negative to start with, we need to take something to take care of the fact that the square root of x squared here does not equal x. However, the square root of x squared will always equal the absolute value of x, even if x is negative. So if our solution has a variable to an odd power, remember anything to an even power still is even, so we don't have to worry about that. It's these negatives that we might crop up. We need to use the absolute value symbol. All right, so let's look at a few more of these. The square root of x cubed is, again, looking for those perfect square factors. The square root of x squared times the square root of x. The square root of x squared, we've already said, is the absolute value of x. The square root of x to the 4th. Now this is x squared times x squared, which is going to give us an answer of x squared And since that has to also be positive, we don't need the absolute value. Even power is okay. Odd power, in this case a 1, it needs an absolute value. All right, what about the square root of x to the 5th? Well, that's the square root of x to the 4th times the square root of x. So again, x squared root x, we're fine. Square root of x to the 6th, that's x cubed times x cubed. X cubed is an odd power, so my answer needs an absolute value. Okay, so keep that in mind when we get to variables. Let's do one more example. It's a little bit of a lengthy one, but I think it'll help put everything into perspective. Okay, the square root of 60x to the 5th, y to the 6th. First of all, we need to deal with the 60. Square root of x to the 5th, square root of y to the 6th. 60 is 4 times 15, which is 2 root 15. X to the 5th is x to the 4th times root x. And this is the square root of y to the 6th still. So that's x squared root x, even power, we're fine. Y cubed needs absolute value. The last thing I'm going to do is put all my radicals to the end. So I've got a 2 and an x squared and an absolute value of y times the square root of 15 times the square root of x. And using my product rule, I can put that back under one radical. So there's a lot going on here. Look at it another time. We'll do some more samples in class. The quotient property. The quotient property, very much like the product property for any numbers a and b, the square root of the quotient is equal to the quotient of the square root. So again, I can take a fraction under a radical and split it up into 2 pieces. I've done the same thing here with numbers. You notice that the denominator, square root of 36, can be simplified just to 6. So most of the time we can just take the square root of each piece and simplify it out. Now, sometimes we need to do something called rationalizing the denominator. Simplified radicals may not have a radical in the denominator. So if I have something like this, and neither of those can be simplified, I'm going to rationalize the denominator. And all that means is to multiply the top and the bottom by the radical in the denominator. Root 10 times root 3 is root 30. Root 3 times root 3 is root 9, which then can be simplified to 3. Let's try another one. I'm going to multiply this by root 6 over root 6, because then when I multiply my denominators together, I'll get a perfect square. On top, I get the square root of 12. Again, simplifying, I will get 2 root 3 over 6, and 2/6 is the same as 1/3. Okay? So a simple radical in the denominator. To get rid of it, I multiply the top and the bottom by the same radical. Let's take a look at conjugates. Remember our conjugates. Conjugates with radicals. Again, plus minus, same as the front and the back. If I use FOIL, first times first, outside is negative 3 times root 2. Inside is positive 3 times root 2. And last is negative root 2 times itself, which is simply negative 2. Look what happens to the middle. So my answer here is 7. Now you can use the special pattern. You don't have to FOIL it if you remember this. The special pattern for conjugates is square the first, square the last, and we're done, because the OI always will cancel. So I'm going to use this to simplify more complex radicals. So if I have 2 divided by 6 minus root 3. I can't just multiply by root 3 to simplify. I need to multiply by the conjugate, top and bottom. On top, I need to distribute 12 plus 2 root 3. On the bottom, 36 minus 3. So 12 plus 2 root 3 over 33. And we will do some more of these as well. The last thing to look at is our rules for simplest radical form. In order for a radical to be simplified, no radicands, that's the number under the radical, or under the square root sign, no radicands can have perfect square factors. We talked about that when we took the square root of 12 and changed it to root 4 times root 3. Secondly, no radicands can contain fractions. If I have a fraction, I have to simplify and make sure that there is not a fraction under the radicand. And the last thing is that no radicals appear in the denominator. So if I have something with a radical in the denominator, I have to rationalize it. In this case, I have to use a conjugate because it's a binomial. Distribute the top. The bottom is 1 minus 2. So I get 3 minus 3 root 2 over negative 1. And I can, as with any fraction, if I have something over negative 1, I can just change it to negative on top. So negative 3 plus 3 root 2, I changed both signs, and I've taken care of things. I know there's a lot,